supported the appointment in the School of Computing and Information Sciences at FIU. He received his PhD in computer science from the University of Maryland, Baltimore County in 2005, and joined the Department of Computer Science at Southern Illinois University as an assistant professor. Dr. Akaya was an associate professor at SIU from 2011 to 2014. He was also a visiting professor at the George Washington University in fall 2013. Dr. Akaya leads the Advanced Wireless and Security Lab at ADWISE in the ECE department. His current research interests include security and privacy, Internet of Things, and cyber physical systems. Dr. Akaya is a senior member of IEEE, is the area editor of Elsevier Ad Hoc Network Journal, and serves on the editorial board of IEEE Communication Surveys and Tutorials. Dr. Akaya was the general chair of IEEE LCN 2018 and the TPC chair for IEEE ICC Smart Grid Communication. He has served as the guest editor for many journals and in the OC TPC of many leading network security conferences, including IEEE ICC, Globecom, ICNP, Infocom, LCN, and WCNC, and ACM WISEC. He has published over 230 papers in peer-reviewed journals and conferences. He has received the top cited article award from Elsevier in 2010. Thank you again, Dr. Akaya, for accepting our invitation. The floor is yours.
No, thank you, Hadi. You didn't have to read all of them. I just gave that for the email. But thank you. So I wanted to give a number of projects, so I put everything on. Try to put everything under one title, the IoT related title. So it's challenges of IoT when you consider broadly cybersecurity, and under cybersecurity, I picked key management, cryptocurrencies, and digital forensics. So there will be 3 different projects that I will be talking about. But before that, let me give some background for those who are not familiar with IoT. Perhaps you have already heard IoT and know IoT, but this has been a hot area of research for the last 20 years, and I just want to give some current status. So here and now, what's happening? So we already know that the IoT devices are being used right now, and even in our homes, we have a lot of IoT devices like smart watches, sensors, smart meters, glasses, etc. And there are many IoT devices used worldwide. This number is changing every year, but the last time I checked, it was around close to 6 billion IoT devices. And there are different domains that these are being used. And you see here, I listed some: transportation, homes, health, agriculture. So this means that it's not just research. Research is almost done at the fundamental level. And now we are actually witnessing this IoT era. So going back to research, just to recap what has been done so far, you see on the left is a IoT device with its components and its interactions with other layers. So there's hardware and software layer, and there's communication layer, etc. And on the right is the mostly IoT network infrastructure. When you have IoT devices, you want to collect data, and that is done by the sensors or IoT devices at the perception layer, and then that is sent to cloud through the network infrastructure. So there's a 3-layer infrastructure that we see for IoT. And when you look at the research agenda here, so far over the last 20 years, there has been a lot of hardware related research on building these devices, smart and energy efficient IoT devices like CPUs, radio, sensors, because these are all battery operated in many cases. So there has been a lot of research on that. And then there's a huge amount of research on the wireless communication aspect of it. And then there is, of course, security and software related research. This is also huge. And finally, now we're seeing a lot of data analytics research related to IoT, because we collected a lot of data already, and we want to analyze this data for the good of the society. So under these, when you look at, okay, what was achieved over the 20 plus years, I remember this started even before 2000 with the name sensor networks. And then as a graduate student, I work on sensor networks, and I witnessed actually this, this trend from theory to product in our homes. This is actually fascinating for me because I remember in early 2000 when I was working on this concept, it was like, you know, music to the ear, but now we're witnessing that we're using them. And this happened because of the really excellent research that was pursued during these 20 years. And if you look at it, I was just mentioning those categories in the previous slide, that there was a lot of achievements in terms of energy efficiency, resource constraint, design of IoT hardware, a lot of communication protocols, like, for instance, today, we're using Zigbee, LoRa, in addition to Wi-Fi, of course. Bluetooth was there before, but these Zigbee, LoRa standards that just came after when IoT was introduced. And then you see a lot of Android, iOS applications, new programming platforms just to program these devices. And of course, the cybersecurity and privacy aspects are huge. There has been even a lot of standards now that solve these problems of security in communication or at other layers. And then now we're seeing this real-time processing of the data collected from IoT devices, either at the edge or at the servers on the cloud by using machine learning. So these are already done and still being pursued, but fundamentally, I think most of the research is done. And when you look at the spending, I said that they're already deployed. So this is numbers for 2020, but you see how much spending on different categories like manufacturing and transportation are leading. And there are many other categories that are utilizing IoT already. So this means that we will see more deployment of IoT and more, probably more new applications, not just these listed here. So where do we go from here? We see that, as I mentioned, we see that we already researchers studied most of the fundamental problems. And due to that, specific IoT applications are realized today. So to me, next level here is to bring IoT to masses. That means IoT right now is being used by specific companies or specific people, but we want to bring it to masses. That means like computers. When we started to use internet in 1990s, internet was not common, right? So, but after early 2000, everybody learned about internet and everybody was using a PC. So we want to, I think, experience the same thing with IoT, that we want to bring it to even ordinary people, like senior people would like to use IoT, and they should be able to use it. And I see a lot of potential there, and hopefully in like health applications, agriculture, transportation, environment. In these fields, we will see that trend. But in order to realize that trend, I think now the research is a little bit different. So it's not really fundamental, but maybe it's more on the engineering side, like how to design these systems for the needs of the applications. Or if it's a different domain, a different discipline, how to deal with interdisciplinary challenges. Or how to, when after you deploy these, how to manage the IoT devices, how to manage their security. This might be more interesting. It's like IT management, right? So we have lots of computers and huge networks, and we needed people to manage them because that grow as a separate area. And similarly, scalability, interoperability, because lots of companies, they're getting into this, and we need to deal with these type of challenges. I think Big picture is here. So if you're a student and like you're interested in IoT research, I think these are the items that you may want to explore rather than getting into the fundamental problems, because it's very already heavily saturated in terms of research. So I'll give you some examples on what we are doing in our lab on IoT. Of course, there are other projects that are not related to IoT. I will talk about them at the end, but I want to just briefly mention some of them. And since there will be multiple projects, probably I will not get into all technical details, but I'll just give you an idea of what we are doing so that if you're interested, we can talk about them later separately. So I'll start with the security management use case. This is about security, and I already mentioned that there is already security solutions because IoT is used in critical infrastructures now, right? Like smart grid, for instance, or smart city applications, or other cyber physical systems, maybe transportation, right? So in such applications, you need to deal with scalability, and you need to, of course, offer security. This is by default should be there. You cannot escape from it. So when you offer security, of course, solutions are there, but the problem is you need to manage it, right? Management means, like, for instance, one aspect here is the key management. So when you have security protocols, you would need keys, definitely, to do encryption, authentication, whatever. And these can be symmetric or public keys, if you're familiar with the key types in security. And those keys should be created, distributed to devices, and then renewed, right? So this is part of the management. And this is a different problem than, for instance, let's say you're doing cryptography, right? So that's more on the theory side, but this is more on the management side. So let's, for instance, consider symmetric key management. Symmetric keys are keys shared between two parties. And in case of IoT devices, we want to provide scalability. Keep that in mind, right? So we are talking about thousands of devices that would need to be managed in terms of, so you need to distribute them the keys, you need to update their keys. So that means they need to exchange a lot of messages to do this, and they need to also do computations, right? So for computations, there has been a lot of research already. Lightweight cryptography, for instance, this is an area that focused on computational solutions that do not require a lot of resources, and many IoT devices lack resources, right? So it has been studied. What we studied here is most on the communication aspect, and this is due to the limitation in the communication channels. So of course, we have Wi-Fi, we have 5G, we have a lot of really high bandwidth channels that we can use for IoT. But in many cases, the IoT devices use channels with less bandwidth because their data is not really, like video streaming. It's mostly text data, right? So they don't require a lot of, they're not bandwidth hungry. So that means you may use technologies like Bluetooth, Zigbee, or LoRa. These are in the order of kilobits, and they will be enough. Or in some cases, you will see legacy infrastructure. For instance, this is the case for power grid. They use 2 or 3G. So we are now at 5G, right? In the past, there was this 2G, and 3G still exists, but 2G, I think it's not. Doesn't exist anymore. But these guys use this. These are very old infrastructures, and they may even rely on something called power line communications. These are really very, very limited in terms of bandwidth. Now, when you are sending data on these channels, and now you want to have security, you want to share keys, exchange keys, and update keys with many devices. So that introduces a problem in terms of the overhead. So that gives us this challenge. How do you do a message efficient key agreement and renewal? for those environments. And I will give you this smart grid use case. This is a use case that we studied with a utility company. Actually, this was part of a Department of Energy funded project. So when we talk about key management, they came us and they said, well, we're using 2G for reaching out our devices in the field, and these are hundreds of miles. And when we would like to update these keys, basically all of them at the same time would create a lot of traffic that it disrupts normal data traffic. So the channel is occupied with the key management overhead that our normal traffic will be delayed. And in some cases, that normal traffic, especially in smart grid, might be really critical. So there's a reliability risk here. But at the same time, since they don't have the resources, there is a security risk, right? Because they said, well, we're not changing the keys. You know, we just assign the keys initially, and then, you know, we keep those keys so we don't change them. Normally, in a secure practice, you need to change the keys frequently, right? And there are many protocols that require keys. You see the list of standards for smart grid communications, and these are typically in this infrastructure. Well, you have a control center, and then there are many remote devices, and you connect them through wireless, through this radio link, which is typically low bandwidth. So, so we knew that the symmetric key exchange problem is a well-known problem. I mean, on internet, you have solutions for it, right? So there's TLS. As part of TLS, there's Diffie-Hellman, they are using it, or there's internet key exchange. This is part of IPsec protocol. So they have a key management system as well. So these are already studied for internet. And there are standards, right? So if you look at the standards on the right side here, there is TLS, which is we are using today, right? TLS 1.2, 1.3. 1.2 was improved in 2018. And you see here the 1.2 protocol. And you see this round trip time. So round trip means from a client to server, is one RTT. And when you would like to agree on a key, you spend 2 RTT for TLS 1.2. And this is also true for IKE version 2. And they improved it to 1.5 RTT in TLS 1.3. So there is already some solutions if you want to just create the keys, right? But of course, these are not really suitable for our case that I mentioned, because they assume that, okay, this will be run on internet, right? They need significant resources, but we don't have those resources on smart grid, so we cannot just take them and use them. So what we did was to come up with a protocol that's going to be customized for the needs of the environment that I mentioned. We'll combine Diffie-Hellman. Diffie-Hellman is there. That's the fundamental key agreement protocol. But we added this hash chaining idea so that we can achieve a 0 RTT key exchange. That means in the first message that I send, I can have my key, encrypt my message, and start sending my data, right? The first message. So this way, you won't have overhead of sending messages and keeping the channel busy for agreeing on a key or for renewing a key. And this is also authentication, providing authentication and replay attack because of this hash chaining that I will just describe. And it's first replay attack resistant 0 RTT key exchange protocol. The replay attack feature does not exist for TLS 1.3. So we published this, you see here in 2019, and then we extended it, and we have now a journal version. But I will just give you the initial protocol. So there are three phases. The first phase is the setup and configuration, where you have your IoT devices in the field, and then they are sending their configuration parameters to a control center. This is done only once. And then once you set this up, then they can agree on a key, and continuously they can renew that key. And this is the typical Diffie-Hellman key exchange session. This is well known. So basically, if you want to agree on a key, there's these parameters that you need to you randomly come up with a parameter, and then you get another public key from the user B, and then use that public key with your random key. And if you get this power modulus Q, that will give you a key, right? So this is used a lot, and we are still relying on the same mechanism. The only difference is, as I said, is this idea of using hash chaining. So hash chain, what we mean is basically we have hash functions, right? So if you get a nonce, a random number, and you hash it multiple times, let's say n times I'm hashing it, so that will give me a parameter called s to the power n. So si belongs to a field device I, and it is hashed n times. So it's like hn, hn minus 1, n minus 2. So it's like actually a chain when you open it. So what happens is this control center will create those S values for every field device. So if you have n field device, we will create for each of them. And it will also create this Y value, which is the Diffie-Hellman parameter for each device. And then we'll send them to each device in advance. So these devices, see, these are the field devices. This is the registration phase. They need to get these parameters, and then they can set up a expiration date or update time. That means you want to use this Y value that came from the control center for a certain amount of time, and then after that time, I will need to renew it for security purposes. Or you can maybe just ignore the update time and just rely on n parameter here. When n goes to 0, you need to get a new one, right? So it's up to you on how to set that policy, the company. So what happens in the protocol is that since they have this parameter y from the control center, they can just create a key by picking a random number a, and this key is created, and that same key is used to encrypt the data from the client side, and that is sent to the control center, and the client also sends here this hash chain s to the power n for client I. This is important. That's actually the deal here. The main deal here is, well, we send this parameter, and control center will check whether it has the same parameter stored in advance for that device. And if they match, this means that, yes, that's the same device, and this is also like a counter for replay attack. And it will accept it, and it will also send a reply, which will use the same key. This same key can be generated here because this parameter x is also sent to the server. So the same key is sent, but the trick here is now it is updating the hash chain because you cut one of the hashes, right? So it's now s to the power n minus 1. So you send it to the other side, and this goes on and on. This way, the other side will do the same check here. You see, this is when you receive it, you need to check n to the power n minus 1 to make sure that it's coming from the control center, and there's no replay attack possibility here. So this way, there's a mutual authentication of devices and the control center to each other, and there's no replay attack. And you can use the same mechanism to refresh the keys. Basically, to refresh the keys now, you would need a different Y value, right? I was mentioning this Y value is initially given to you, and at the expiration time, you need to update it. So you start from scratch, you send a different Y value. But until getting that Y value, you can still renew the key without updating the Y value. So you can, basically, it's just picking another random number and another key will be generated. So this way, for each transmission, you will get a different key from the client device to the control center. So this was actually based on TCP when these messages are sent. Basically, we want to make sure that the messages are not lost, right? Because it's wireless communication and it's limited bandwidth. So if you use TCP, obviously it comes with a lot of overheads, and TCP has its own reliability mechanisms, connection establishment for those who are familiar with TCP. So that actually adds more overhead, and we wanted to see if we can design this by using UDP, because if you use UDP, that the overhead that comes with TCP will not be there. But of course, you cannot guarantee reliability of the messages, and you need to have a mechanism to ensure that reliability. So what we did is we used UDP. At the application layer, we introduced reliability services. So we introduced our own sequence number, retransmission counts. This is actually another big project that I'm not talking here, but it's a new protocol, and we proved that it's working and we implemented it. I'll just show you the results of implementation of this, but it's actually extended and submitted as a journal paper to IEEE transactions. So for evaluation, okay, so now we have the idea. We want to evaluate this. How do we evaluate this? There are two ways that we do evaluations in our lab. One is, obviously, you can create a test bed with IoT devices if you have access to them, or you can use a simulation environment. So in our case, we wanted to use the protocol LoRa. LoRa is a very low bandwidth wireless communication, or wide area wireless communication standard. So we purchase LoRa dongles that can be attached to Raspberry Pis, and we set up a test bed for it. And then we also had access to networks, NS3 simulations. So we created a simulation environment that is for scalability. And we basically compared the TLS, DTLS, which is the UDP version, and our implementation, our protocol. We just look at the total completion time of, like, when you want to agree on a key, how long does it take? So the LoRa testbed here just shows you how it was created. You know, you have Raspberry Pi devices. We put the LoRa gateway, and it's connected to Amazon. And the communication was happening here, right? The wireless part. And then we also created a NS3 environment where we have a LoRaWAN channel, but we bridge that to our client and server, and we basically use NS3 features here, the LoRa channel with the LoRa channel. And the other thing that we could do here is generating background traffic. So it's like when you use this channel, it's not specific to LoRa. We need to generate other devices that are using the same channel, right? So eventually, that's just, I want to summarize the results here. There are actually two settings that we tested, PKI and PSK. PKI is the certificates, PSK is the pre-shared key settings. This is faster normally. So when you look at the results, say, let's look at the PSK results here. So here, our approaches are these two, right? TCP 0RTT and UDP 0RTT. So you see that both are much better than the other ones. And the UDP one is actually the perfect, right? So here, especially, it's the best one. And the same pattern in the PKI settings here with some, variations. We check whether this holds for simulations as well. So for simulations, we have seen that the same pattern exists with different amount of background traffic. So eventually, our UDP approach is best here, and even in the worst case, it can provide at least 4 times reduction in time. So that means if you have lots of IoT devices doing this at the same time, the gain will be much higher, and this will be suitable to use in those low bandwidth environments. We actually applied to a patent, and we finished the disclosure, and we just submitted the patent documents for this, and we're waiting for the patent. Now, the other project that I will talk about is about cryptocurrencies. So this will also be linked to IoT research that we are doing. The cryptocurrencies, I'm sure you've heard Bitcoin, and there are many other cryptocurrencies similar to Bitcoin that are coming, and we're witnessing this era. So this is like the beginning of IoT era in the early 2000s. But mainly this was driven by Bitcoin. It was in 2009, and the revolution there was the distributed architecture, data structure called blockchain. All right, so it helped us to revolutionize the way payment systems can be designed in a distributed manner. And now we have seen a lot of applications of it, blockchain, but there's a lot of use of Bitcoin. So when you look at it, Bitcoin is dominating the market. Still, it's like 50% of the existing cryptocurrencies. There are many cryptocurrencies, maybe more than 6,000, but Bitcoin is the top, right? But the main issue here with Bitcoin is that you need to wait for the transaction validation times, which takes hours. And they have a system called proof of work, right? And this is about finding the right hash. So you need to wait for the transactions to be validated. And then there is also, of course, a transaction fee that you need to pay. Of course, if you are doing a micropayment, that means, like, let's say you want to buy a coffee, right? That's not possible because it will take time and you'll need to pay fee, right? So this is not attractive for micropayments. But if you have like large transactions, then yeah, you can use Bitcoin. So in order to address these two issues, they came up with a solution called Lightning Network. This is actually on top of Bitcoin. So if Bitcoin is first layer, Lightning Network is on top of it, and it is addressing this the transaction validation time and the fees, right? So it makes it more scalable, and now it has, this is I think a snapshot of the number of users and channels. So there are maybe more than 10,000 users now. This started in 2018. But the idea here is based on a concept called off-chain. So off-chain payments means when there's another party you are doing transactions, you're not writing everything on blockchain, but you are creating a channel on Lightning Network, and you are making a lot of payments, but you're not writing them to blockchain. The only thing that you write on blockchain is the channel opening and channel closing, right? So whatever you do here will not be subject to that proof of work. So it will be a instant validation, and eventually it will give you this opportunity to do real-time micropayments, right? So this is an advantage to be used in a lot of nice applications. And given the emergence of these cryptocurrency payment, they call it cryptocurrency payment networks, by the way. In general, the Lightning Network type networks are called cryptocurrency payment networks, and they're second layer. So given this popularity, it comes also to IoT that if you want to make a payment through an IoT device, because in some cases, IoT devices might need to make payments for services they are getting, or they're providing services and they need to be paid, right? So the challenge that we were looking at here is if an IoT device would like to make a payment with Bitcoin, is this possible? Well, in order to do that, you need to have Bitcoin support, like you need to have it on your computer, and there's computations, right? So computationally and storage wise, this is not really possible with a lot of IoT devices because they don't have storage. So it won't be possible to do this, to download this everything on IoT device and run Bitcoin, right? So is there a way to run Bitcoin or have access to Bitcoin through IoT devices? This was our challenge. And then we realized that there is a concept called machine-to-machine economy, or you can specialized version might be machine-to-machine crypto economy. So basically you have these IoT devices, the machines, and they talk to each other, right? We have that infrastructure. They can also make payments to each other. So there are a lot of examples of this, like for instance, you're charging your electric vehicle. So the payment can be automatically done when you do this if there is a payment mechanism, or you're parking, your car can pay for you. You don't need to pay it separately. Or let's say your vehicle, this is actually a nice example, is passing through a toll, right, on a road. Then we have these RFID devices, and then they actually charge it, but it links to an account, and you enter your credit card information. In this case, for instance, you may have a device which will pay for you automatically when you pass through the tolls, right? So you don't need to enter any information if it's like, let's say, through cryptocurrencies, let's say Bitcoin, right? So you make your toll payment through Bitcoin, and it's just done by the car on the device, and that's it, right? So you don't need to deal with anything. So there are many cases here that can be considered, especially with automated vehicles, automated trucks. This will come up. We have seen this in some applications. So overall, we call it the machine-to-machine economy. And actually wrote a paper on this, a communication magazine paper, and it was really well received, and it's coming up. So what we want to do then here is, okay, consider an IoT device. I want to make a payment, Bitcoin payment through my IoT device. So you have something like this. Your IoT device is here, right? And you want to make a payment through the Lightning Network, because Lightning Network is fast, right? So we want to make Bitcoin payment, but Lightning Network is our preference because it's fast. So this blue thing is the Lightning Network, right? So what we do is we send it to a gateway. This is a Lightning Network node that we have maybe an agreement in advance. And then from there, it will be paid to the destination. Let's say you're paying the toll, and there's a toll server here, Lightning node, right? But IoT cannot be part of this Lightning Network. We mentioned this because we don't have storage and computational capability. So what we propose here is, let's find a gateway. Normally, if you trust the gateway, you're fine, right? I mean, you can just send it to the gateway will pay it on your behalf, right? But in real world, we cannot trust the gateway. So we want to come up with a mechanism that will ensure this trust through the IoT device and gateway. So we propose something that relies on threshold cryptography. So basically, threshold cryptography gives us the opportunity to work with the IoT device and the gateway together, and they sign the transactions together. So there's, for instance, 2x2 threshold scheme. And that means we will run a threshold client on the device and then a threshold server here on the gateway. And then they agree on a key, and then they sign together. So it's not gateway by itself, but it's getting IoT's share and signing it. So that's actually part of the threshold cryptography. It's distributed to more than one parties are involved. So basically, roughly, you can say the key is divided into multiple pieces and shared among parties. So in our case, it's between the IoT and gateway device, and they co-sign the transaction. So in this case, you don't need to trust the gateway because you are already part of it, right? The signature. They will give you the link to it, right? I mean, the signature has also your, the transaction signature has also your piece in it. So we use threshold key generation, threshold signing 2 by 2 because we have 2 parties here, and key derivation from the existing literature. And this is our threat model. You see, we are assuming the gateway might be malicious, and then there might be collusion among the gateway and this bridge LN node. This is the node that the gateway needs to create a channel to start sending data, money, I'm sorry. So what we did was to revise the protocol of Lightning Network so that we can integrate this IoT piece. So there are three main phases in the LN when you want to send money. So you need to open a channel, send your payment, and then close the channel. So we need to integrate the IoT portion here. So our protocol modified those phases, and it's called LN Gate. This was published in WISEC, ICM WISEC just last summer. And this is a summary. I don't want to, I don't have much time. I just want to summarize what we did here. So this is the opening, channel opening, right? So the IoT device is basically saying the gateway that, hey, can you open a channel on my behalf in the Lightning Network? So these red messages here are already part of the Lightning Network. What we introduce is the green messages. So there is a protocol among IoT device and LN gateway, and they first create a shared key. This is a threshold key generation algorithm is used here. And then that is used to sign the signature to open the channel. And then same for the payment. So if you want to make a payment, then you sign with this the keys, threshold signature with IoT device and LN gateway, and closing same. So we have the security analysis and how to deal with. There is a revoke state broadcast concept on how to deal with it. I just want to quickly move on to the experiments. So basically, we implemented this as part of, there's a C Lightning node for running Lightning Network. That's open source from Zango. And that's actually, there was a guy from that organization that helped us in this. We work with them together. So the code is available publicly and on GitHub that can do this threshold signature. And then we implemented and tested this on a Raspberry Pi, connecting to a laptop and sending messages as if the laptop is our gateway. So mainly what we were looking at is what is the overhead of the threshold key generation and signing. So the key generation is the problem. It takes time. The signing is not a big issue. See, it's like 153 milliseconds. So when you look at the, let's say you want to make a payment, right? So for the payment, you need to first request the gateway that, okay, do this payment for me. And then it will open a gateway, a channel, and then send the payment, right? So these are done together. If you don't have, let's say the gateway is doing this payment, there's no threshold, there's no IoT, then it's very quick, right? So it's 0.2 second, 1.4 seconds, just opening the channel, sending the transaction, right? But when the IoT is involved, it takes more time. So we would, of course, the channel opening is just done once. So if you focus on the payment time, there is like this 4.1. So it's around 4 seconds versus 1.4, right? That's the additional delay that we get. And when we consider a toll application, for instance, let's say you're passing through a toll and you want to make a payment here. Of course, this is a wireless connection, and let's assume that you have Wi-Fi. And let's assume that the transaction range is about 250 meters. So you're coming with the speed of 80, and you're passing, of course, you're slowing down, but you're passing through that toll. So you are within the range of Wi-Fi, and we found out that you have probably around 7 seconds to complete the payment, because otherwise the car will get out of range, right? So if the payment time is 4 seconds, then this is reasonable. And we did a lot of experiments on different standards and speeds, etc. But this is a nice case where you can see that this is feasible. And finally, I would like to talk about the last project we did with IoT is the forensics. This is an interesting area that is emerging because there's a lot of now applications where you collect data through the IoT devices, and those applications are critical. For instance, like vehicles or drones or some other cyber physical system applications. So when you collect data, that data might be used later as an evidence in the disputes. Like if there's an accident, how do you prove who is at fault, right? So that is that you need to go back and find out, what happened through the IoT devices and sensors, or your drone camera is recording something, and you need to go back and prove that recording came from the camera and it was not changed, right? So there is this integrity issue here, especially this, I have seen a growing interest on vehicular forensics. And actually we wrote another paper, it was a magazine paper, and it actually received lots of citations in 2 years. So in this work, what we did, we work with a local company. They were doing this boat rentals, and it's called Boatrax Incorporation. So there are rentals, right? So when they rent the boat, they want to make sure they put sensors and monitor the boats. They want to make sure that the renter is complying with the regulations and they're not getting out. There's GPS, etc. So if something happens, let's say there's an accident, and how do you know that who is at fault, or maybe where it happened, etc. So in order to prove those, you need to come up with data that is going to be accepted by the court, and they don't accept the data because it may be changed. So the insurance companies are like this too. So if you use something like a blockchain, it will guarantee the integrity, and this might be accepted in the court or the insurance companies. So what we did was, so they have a system where they feed data from, there are sensors on the boats, and they feed data to a company database through MQTT protocol. So what we did was, okay, we want to get the interesting data from these boats and store it in blockchain. Blockchain is chosen because you cannot, once you store it, you cannot change it, you cannot delete it, right? It's an append-only structure. And there are public and private blockchains. Public ones are more secure, but the challenge here is you need to pay for it. So for any transaction, you need to pay. So the storing of everything will be costly. It's not like you're storing to a local database, right? So what we did was to come up with a solution that will do a multi-chain approach. Of course, you can just say, hey, I can just put the hash of the data, right? But this is data coming every day and from many boats, so it's still huge data. So we wanted to create a multi-chain approach and store it in blockchains that are cheap, but we also wanted to make sure we have a copy, a sort of a copy in the public strong blockchain like Ethereum. So this was published in a conference on blockchain and cryptocurrencies last year. So basically, this is the idea. So you get the data, of course, not all the data, that's just significant data. Store it in the database, but at the same time, you store it into two blockchains that are cheap. In this case, we chose Stellar and EOS, but of course, this can be changed. So you can choose others, increase this. But eventually, the hashes stored here are still huge. So what we want to do is we want to get the hash of hashes and put it in Ethereum, because this way Ethereum is costly, and this way you will just put the hash of hash. So it's like very limited data, and for hash of hashes, we propose something called Merkle tree, and this is a very well-known structure in security that you can see these are your transactions, and you can hash them, and there's a hierarchical hashing, and when you hash these two, you get this, and then eventually there's a root that is created. So that root is stored in the Ethereum blockchain, right? So if you want to verify it, of course, you need to know the root, and you need to know these green hash values. For instance, like for transaction 4, if you want to verify it, you need to know hash 3, hash 1, 2 here, and the root. You don't need to know the others. So the amount of information that you store will be much less. So we did this, and the verification is easy. Of course, the first level blockchain, you can directly check the hash and compare it with the database data. The second one is through the Merkle tree verification, and this is what we have, right? So the data, transaction, Merkle tree, root, and the path nodes, like these red ones, are stored in the database. Not all of them, because those are used to do verification. So eventually, I just want to show you the costs of using this platform. So this is the time to write to those platforms. The costs, we assume that, let's say we have 1,000 boats, and there is data coming every day, and this is the number of hash values we write per day. And for that, there's a cost, right? So when you consider our approach, multi-chain approach, the cost is this. But if we assume that we store everything in Ethereum without Merkle trees, then the cost would be this. So it's huge, still huge cost. So this saved us a lot of money here if you go through this multi-chain approach. Anyway, so I'll stop. The research part is done. I'll just mention other projects here that for those students who are interested in working with us. We do a lot of key management still. We now want to do group key management of the research that I mentioned. This is part of, there's a NSF IUCRC center. We want to do post-quantum key management. This is part of NSF CREST Center with the Institute of Environment at FIU. Machine-to-machine economy concept that I mentioned, there are lots of other things that can be done. We want to work on it. We have a project on drone forensics as part of this Digital Forensics Center run by Computer Science and RAMS Center. So we're doing drone source camera identification by using images and video, using machine learning and deep learning. We want to do drone fingerprinting as part of that project. There is something called secure multi-party computation. This is part of Air Force research project, but we want to run it on machine learning applications and among IoT devices. There is a cryptocurrency forensics project with NSF CART Centers for investigating cryptocurrency artifacts. Payment channel networks, lighting network, this is also going on. There's an interesting need here, 5G security. I do 5G security and I need students on this with IDEO National Labs. There is this open radio access network security, device-to-device security as part of this new standard, and then testing of the standards. There's an NSF project on automated vehicles using software-defined networking. This is already going on. There's a new one funded by NSA, again, using SDN and machine learning to do network defense. And there's a lot of training related activities. So if you're interested in cybersecurity education at all levels, we are interested in that. So there are projects, for instance, for public sector, there's a project, NSF project, that we do cybersecurity training. Cisco funded project is doing IoT and hospitality training. USAID project doing SCADA security training in Ukraine. And then there's University of Washington is leading this NS3 project, and they want to bring NS3 to education for undergrad or grad courses. So this is my information. If you'd like to, get more details about us and my email, my lab. So I'll stop here. I know I'm out of time. So I'll be happy to answer questions in the remaining time.
Thank you, Kamal, for the interesting talk.